Hello, everyone. Welcome to Chapter 5. We're going to look at z-scores, normal distributions, and then the standard normal distribution in this section. So to start things off, I would suggest giving this problem a try on your own by hitting pause and just reading through it, and then make a decision about candidate A or candidate B. Basically, there are two candidates that have taken different tests, and you're deciding based on those tests which one you would hire. So give it a go, and then I'll continue. So what you're going to be looking at here is the relative position of the candidate based off of the mean and the standard deviation. Candidate A, there was a mean score of 742, a standard deviation of 28, and they got a 801. So what you want to be thinking of is how many standard deviations above the mean was the candidate. To figure that out, we could first subtract the candidate's score minus the mean, right? That would give us the difference between those two. And then the number of standard deviations can be found by dividing that by the standard deviation. This would give me the number of standard deviations above the mean for candidate A. If I calculate that, getting out my calculator, I would do the subtraction first, which is 59, and then divide that by 28, and that's about 2.11. And then I would do the same thing for candidate B. So I would take the candidate score minus the mean, divide by the standard deviation. So let's see, 94 minus 67 is 27, and then divide that by 12, it's 2.25 exactly. Now I have something I can compare. I couldn't really compare their scores in the raw form, right? Because they were just based off of different tests with different means. So it didn't make much sense to compare those scores. But now I have normalized it, and now I have something I can compare. So candidate A was 2.11 standard deviations above the mean, while candidate B was a little bit more above, 2.25. So we would take candidate B as having a better relative score relative to those that had taken that test. This idea has a name. It's called a z-score. So these are what we're going to call z-scores. A z-score is a position relative to other data values in a distribution based off of the standard deviation and the mean. Okay, so here's a more formal definition. Right? A z-score measures position, and it indicates the number of standard deviations from the mean. Here's a formula for it, which is basically what we just did, right? We take the raw score x, subtract the mean, and divide it by the standard deviation, sigma. Okay, typically we're going to round these to 2 decimal places unless otherwise stated. So here's another example. Student A got a score of 53 on an exam, while student B got a score of 70, let's say on that same exam. The class mean was 58 and the standard deviation was 4. Let's see if we can find the z-score corresponding to their raw test scores. Okay, so for student A, I take their score, subtract the mean, and then divide by the standard deviation. So 53 minus 58, notice that that's negative, and that matters, right? So 53 minus 58 is negative 5 divided by 4, and that's going to be 1.25 negative. Okay. The other student got a 70, so same kind of form. 70, I should do z equals 70 minus 58 divided by 4. So just make sure you're always doing that subtraction first and get an answer. 70 minus 58 is 12, and then divide that by 4. That's exactly 3. Okay. And what is the interpretation of what I'm finding here? What does it tell you? Well, student A, negative 1.25 means they were 1.25 standard deviations below the mean, while student B was 3 standard deviations above the mean. When you get used to what standard deviation and z-scores tell you, you'll notice that a standard deviation, a z-score of 3 is highly unusual, or unusually high in this case. So that student did very well, okay? Typical values like a negative 1.25, okay, you're in with the pack a little bit on that one, but still below the mean. Okay, the next idea is what's called a normal distribution. Normal distributions are used to model many types of real-world data. Here's some examples. Generally, what we're noticing here in normal distributions is you have this shape that's a bell, right? This nice symmetric bell-shaped look. Okay, so you can explore these. You know, these are rolls of dice or birth weights. So we just noticed that when we graph these histograms, we see that shape. We see it over and over, and we give it a name. It's called normal distribution. Okay, here's some properties of a normal distribution. Now, the mean and the median and the mode are all equal, right? Bell-shaped curve is what we're going to call it. Symmetric, kind of equivalent on left and right sides. The total area under the curve is 1 or 100%, like we saw with the empirical rule. And the curve approaches but never touches the x-axis. So as you're going down here, it's getting closer and closer to the x-axis, but not touching it, okay? We've seen this kind of setup before as well. Adding and subtracting standard deviations, right, to set up the look and label your x-axis in terms of standard deviations. Okay, you might be wondering, you know, what is the equation for this curve? What's the equation of that curve right there? Here's the formula for it. We'll not use it, but if you were curious, like how do you generate that curve? There it is. Something you would do in calculus. What we're more concerned with is some interpretation of the normal distributions in terms of means and standard deviations. So here's a couple of distributions. We can estimate the mean and the standard deviation. So for graph A, the mean is always where the peak is, right? So I'm looking at graph A, peak, it's 15, while the mean for graph B, peak is at 12. Okay, standard deviation is a little trickier, but you're really looking at, if I go back up to this graph, get that out of the way. Here is where one standard deviation is. This point is kind of where the graph turns from curving down to curving back up, right? It's that inflection point there. So that's kind of what I'm after when I'm looking at these graphs, and then I'm estimating that point. So for A, it's probably somewhere in there. So maybe right between 15 and 18, which we can call that 16.5, right? And so if that's 16.5, right, the standard deviation is the difference between 16.5 and 15, which would be a 1.5. So I would estimate that to be about 1.5, or even probably go 2 if you wanted to. Whereas for B, I would say the inflection point would be right about there, wouldn't you say? So right about the 15. So the standard deviation is the difference between 12 and 15. So I'd go 15 minus 12, 3. So that's about 3. And we could look at the shape and link it with the standard deviation, right? Notice with the higher standard deviation, you have a more flat, spread out curve, right? With the lower standard deviation, you have a higher, narrower curve. Now there are infinitely many distributions, right? They're all based off of 2 values, the mean and the standard deviation. When the means and standard deviation change, it's going to change the shape. So they're all bell-shaped, but how high they are, how spread out they are will differ. Now, what we're going to get to next is what's called a standard normal distribution. That's the one where the mean is 0 and the standard deviation is 1. And here's a picture of it. So notice the mean's in the middle, and then here's your standard deviations. Now remember, z-scores are standard deviations above and below the mean. So when we do the normalization, the nice thing about it, on the x-axis are z-scores. When you see cumulative area, that corresponds to area to the left of the z-score. Okay, so properties of the cumulative area for 0 will be this, right? That would be the area to the left. And that's half of the curve, so that would be 0.5 or 50%. Okay. Now, as the z-score increases, goes this way, the area to the left is also going to increase. So the cumulative area would increase. Now, if the cumulative area is at 3.5, which is way up here or higher, right? Remember, the cumulative area is area to the left. So if you're way over here, area to the left is pretty much everything. So it's going to be close to 1. For number 4, there was supposed to be a negative. So this is supposed to be z equals negative 3.5. Don't know what happened to that negative. But the cumulative area is close to, if you're over here at negative 3.5, you're talking about area to the left, it's going to be close to 0. There's pretty much nothing out there. I mean, there'll be something, right? But it's going to be pretty close to 0. Okay. Now there's some different ways that we can use that standard normal distribution and calculate the precise area under the curve corresponding to any z-score. For example, I know I made a mess of this. If we kind of clear it off a little bit, what if I had a z-score of, say, 1.5, right? What is the area to the left of that? And in order to do that, you pretty much have to use calculus. So in statistics, because calculus is not the prerequisite, there are some ways that we can do it. Either you use a table, which I'll get to in the next video, or we'll show how to do it with StatCrunch. Or there's a way to do it with your graphing calculator, which we won't focus on, but I can point you in the right direction for some instructions on how to use your graphing calculator if you have one, if you want to try it that way. Okay, but this is going to allow us to, given any z-score, we can find the area under the curve. And the interpretation of that is, let's go back to that exam. Like, let's say on your exam, you had a z-score of 1.5 for your exam score. What percentage of students did worse than you? Or what percentage of students did you do better than? That's what we're trying to figure out. Okay, so stay tuned for the next video for that one. Otherwise, hope all is well with you, and I'll talk to you later. Bye.